Welcome to qnawire.
All right, in this question, we're referring back to figure 20.9 in the chapter, and it says the cell in figure 20.9 could be used to provide a measure of pH in the cathode half cell. Calculate the pH of the cathode half cell solution if the cell EMF at 298 K is measured to be 0.684 volts. Okay, so we know that the cell EMF is equal to positive 0.684 volts when the concentration of Zn2 plus is equal to 0.30 molar and the pressure of hydrogen gas is equal to 0.90 atmospheres. Okay, and we want to know the pH is what we're trying to find. This question really is just a lot of algebra, honestly. So let's look at the reaction that's occurring. We have Zn plus 2H plus yields Zn2 plus my hydrogen gas. So let's remind the Nernst equation is what we're going to be using in part here, and that's so the EMF is equal to the standard cell potential minus 0. And we're at 298, so I don't need to worry about using the one with temperature. I can just use the standard one, 92 volts over N times the log of Q. So here, if we look at a reaction, we got to figure out what the oxidation and what the reduction is. So here zinc is going from 0 oxidation number to 2 plus, so it's being oxidized. So that's my oxidation reaction. And here hydrogen is going from +1 to 0, so it's being reduced. So if we remember the E naught, our cell is equal to the reduction potential of the reduction reaction minus that of the oxidation reaction. So looking at those values on the chart, I get that this is equal to 0 because hydrogen is their standard, so that's 0, minus a negative 0.76 volts. So my cell potential standard is equal to 0.76 volts. All right, so I'm going to plug all my other numbers in here. So we know E cell, they gave that to us, is equal to 0.684 volts, is equal to the standard, which we just calculated as 0.76 volts, minus 0.0592 volts over N, and we have zinc going from Zn to Zn2 plus, and same thing here, we're two positive hydrogens going to H2. That's a transfer of 2 moles of electrons, times the log of Q. And so what we want to do is here is solve for Q. That's pretty much the only thing we don't know. So you do your algebra, you would find that the log of Q, so I subtracted this over first and then I divided by this, and I get that the log of Q is equal to 2.568. Therefore, Q is equal to 10 to the 2.568, right? If I take 10 to both sides, that cancels out my log. So I get that Q is equal to 369.8. So let's look at what Q is algebraically. So Q is equal to the concentration of my products, which looking back at my reaction, so it's a concentration of Zn2 plus, and then hydrogen, since it's a gas and they've given me pressure, it's going to be the pressure of hydrogen. And those are both to the exponent of 1 because the coefficients are 1, over H plus squared. And then the zinc doesn't go in there because it's a solid. This is what I'm after because that is what's going to help me get pH. So I'm going to solve that algebraically first for H plus. I can multiply the H plus squared over to that side and divide by Q, and I would get that H plus, so H plus squared is equal to Zn2 plus times the pressure of hydrogen over Q, but I want the H plus just regular value here, so H plus is equal to the square root of all that, right? So Zn2 plus times the pressure of hydrogen all over Q. and it's the square root of that whole thing. So I'm going to come back over here, my concentration of H plus, therefore I'm going to plug all my numbers in, and when you plug in all your values, so you have your square root of the concentration of Zn 2 plus, which was 0.3 molar, times the pressure, which was 0.9 atmospheres, over Q, which we found to be 369.8, I get a value of H equal to 0.027 molar. Finally, pH is equal to the negative log of the concentration of H plus, so it's equal to the negative log of my 0.027 molar, and I get a pH equal to 1.6.